Good morning and welcome to this next lecture on sound and structural vibration. We have been looking at a structural acoustic waveguide, and we have gone quite a bit into solving the problem. We were looking at the physics. So at the outset, there is one point I would like to make. This factor, the fluid loading parameter epsilon, is the coupling parameter between the structure and the fluid. If epsilon is set to 0 as we have seen, we get the uncoupled roots. So it's the ratio of the fluid density to the structural density. Okay, and if the medium is like air, a light medium, and the waveguide is made of, let's say, steel or aluminum, then epsilon will be a small quantity, in which case the structure is loaded lightly and also the fluid sees more or less a rigid structure. Whereas on the other hand, if the fluid density goes up, let's say it's water, and there is some light medium for the wall of the waveguide, then epsilon can go up and the situation reverses. So epsilon is the coupling parameter. I didn't mention this explicitly. Okay, there's one more point I'd like to make. This entire derivation on this structural acoustic waveguide can be found in this paper. I'm giving the title, an asymptotic analysis for the coupled dispersion characteristics of a structural acoustic waveguide. This is a paper published in the Journal of Sound and Vibration. Volume 306, the year is 2007, and pages 657 to 674. So there are more details in there than I have presented over here. Now continuing, the equation we have is this: xi fourth over omega square minus 1 lambda square root of omega square minus xi square into tan lambda square root omega square minus xi square plus epsilon, the fluid loading parameter. So this is the equation we use if epsilon is small. However, if epsilon is large, okay, then we have to change. the asymptotic method works for small values. The technique works like that. So, if epsilon becomes large, if epsilon become large, then what we do is we write epsilon as 1 over epsilon dash, okay, where epsilon dash is a small parameter. So, if we do that, we will have xi fourth over omega square minus 1 lambda square root omega square minus xi square tan lambda square root omega square minus xi square plus 1 by epsilon dash equal to 0. And so, epsilon dash comes up. So, I will write this now as epsilon dash xi 4 by omega square minus 1 lambda square root omega square minus xi square. This I will convert it to cot, okay. So, it becomes cot of lambda square root of omega square minus xi square, that is equal to 0. Now, epsilon dash is small, epsilon dash is a small parameter. So, now what is the basic solution, uncoupled solution? If epsilon dash is sent to 0, and my solutions are for cot lambda square root of omega square minus xi square equal to 0. That means the cosine is equal to 0, and therefore, lambda square root of omega square minus xi square, we have seen this solution before, okay, is equal to sum twice m plus 1 pi by 2, okay, m starting from 0 etc. Now, let us say if m is 0, let us say m is equal to 0, then I have lambda square root of omega square minus xi square is equal to pi by 2, okay, which means my xi square is equal to omega square minus pi square by 4 lambda square, okay. These are non-dimensional, this is the non-dimensional y wave number, and therefore, I will write it as ky by kc is equal to pi by 2 lambda, okay. The square root of this is pi by 2 lambda, which is the non-dimensional y wave number, and this is the kc was the denominator for non-dimensionalizing, okay. So, now what is this, which implies ky by kc pi by 2 lambda is kca, so this goes with that. So, ky is equal to pi by 2a, which is twice pi by lambda y, which means lambda y is equal to 4a. We have seen this, if you recall, okay. So, now let us see it again briefly. So, I have this waveguide, top is rigid, bottom lower is this vibrating plate. So, top the pressure will be maximum, so I will come up this way, this 1/4 is the next quarter, This is the next quarter and then the last quarter. Okay, so this is lambda y and this is A, and that's how lambda y is 4 times A, which means again I have 0 pressure here. Okay, so the fluid column sees a medium beyond which is very light here. Okay, there is no gravity, so don't worry about it. Okay, so the fluid sees something very light and therefore the pressure is 0. If the fluid saw something stiff and solid, you will have high pressure. Okay, so pressure is 0 and there will be displacement, velocity is actually high. Okay, so those are the uncoupled solutions here. Okay, and so these are called the pressure release catons. Pressure release catons. So this is called the pressure release boundary condition, where pressure is 0 at the boundary of a fluid. It is called the pressure release condition, 0 pressure condition. So these are the pressure release catons. Okay, and one of the critical points was intersection of this with the flexural wave. We have seen that. Okay, now let me go back to the software Maple, which we saw last time, and I will again show you the demo of Maple and we will get back here. Last time I had shown you the Maple software. So let us start again. So start, this is the basic equation, that's how it looks like. First we will do the plane wave solution. So plane wave solution plus A1 into epsilon, then that trial is substituted into the main equation, a Taylor series is made. Okay, then I convert the Taylor series into a polynomial and then find the coefficient to epsilon to the power 1. So let us do that. Okay, then we have to solve for it, that is the solution to the correction and then the final total answer. Similarly for the flexural wave. Okay. Let us run it. Okay, something changed here, so I will series equation trial series equation trial to epsilon comma 2. Okay, then equation to, yeah, it should work now. So let us start here, trial 2. Okay, then solve it. Okay, then add as a solution. Then third one, this is the rigid caton. Okay, then solve the equation. Then now we will plot it. Okay, so that is the plot. I was trying to get all 3 of them last time. So let us see here, the blue line dashed is the plane wave, this blue line is the first rigid cut-on, this blue line is the second rigid cut-on. This first green line is the uncoupled flexure, this is the pressure release we just spoke about, this is the second pressure release we just spoke about. Okay. So the coupled flexure is just above below coincidence, then here it blows up, okay, and that blowing up is because of the choice of our expansion, not because the actual wave blows up. Okay. Then this is the next coupled flexure, it passes through the pressure release. Okay. We have discussed the physics, that is where zero pressure occurs. So just beyond the wave goes up and just below the wave is below. So you have stiffness effect here, inertial effect here. Again this is the next critical point where the fluid loading actually goes to infinity, and so our expansion fails, which means we have to find another expansion and it will work out. Okay. And so the coupled flexure repeats between every two rigid cut-ons. So again it passes through the next pressure release, above that is higher, below that it is lower, and so forth. Okay. Now the plane wave correction is below the original, below coincidence, this is the coincidence omega equal to 1, and the correction is above coincidence. So the plate is looking like a stiffness here and like inertia here. Okay. As inertia becomes more and more, we approach the plane wave original. As inertia drops, the wave number drops, so that the inertial effect having reduced, the wave speed increases, whereas here it is the other way. Okay. As stiffness drops, the wave number goes up. Okay. So that lambda goes down. Okay. And for infinite stiffness we are back to the original uncoupled plane wave. Now this is the rigid duct, first rigid duct cut-on. So it starts off with this black line, okay, and it blows up here because again of our expansion, and it transitions to the coupled flexure. Okay. So actually it will be a very smooth transition. So the coupled rigid duct comes, transits, becomes the coupled flexural wave, passes through the pressure release point, goes forward, and it latches on to the next rigid duct cut-on. That is how it will happen, okay, as it is doing over here. Okay. Now I will also, so these are now values of small epsilon. So I will show you what happens for large epsilon value. So I will comment this picture. Okay. Now I am doing a pressure release solution here. Let me start over. For this case these are unimportant, but I need to restart the program. I will do the calculation but not plot it. Okay. I have chosen two the second pressure release, so we will see that here, and that is how it looks like. Okay. So So, this is my second pressure release, and this is the coupled pressure release curve. Okay. So, this is a frequency where the particular expansion blows up. So, we do not worry about that, otherwise it will be a smooth curve. So, it is above, below this crossing frequency, one critical frequency, it goes through that point which is the crossing point between uncoupled flexure and that pressure release, and then it transits above, okay, close to the pressure release curve. Okay. So, if I have to show on this graph itself, for small values my curve will be close to the rigid duct. For small values of epsilon, my curve will be close to the rigid duct, okay, and somewhere it will transition to coupled flexure, cross through this point, rise above, follow the next rigid duct cut on. As my epsilon value goes up, okay, I have chosen an epsilon value which is 1 over 0.05, which is like 20. Okay, this is epsilon dash, mind you, from my derivation. Okay. So, epsilon dash is a small quantity in order to find the pressure release correction. So, as epsilon starts to become bigger and bigger, this curve will shift towards the pressure release, that is what has happened, okay, and it will straight away pass through the critical point and crossover. Okay. So, that is the transition from small epsilon to large epsilon. Okay. So, let me get back to my derivation. So, now I will summarize what has happened. So, we have this picture over here. This is omega. Let us see, I will put all uncoupled curves as blue, okay, and light. So, this is my uncoupled plane wave. This is my uncoupled flexure. This is my uncoupled flexure. Then let us say this is my uncoupled pressure release. And this is my first rigid duct cut on. This is my next pressure release. And this is my next rigid duct cut on. Okay. On top of this, let me do the coupled structure. Coupled structure is above here, okay, and at this point there is a transition that is going to happen. A smooth transition, the coupled structure will smoothly transition, become the coupled plane wave. Okay. Below we have the coupled plane wave. It will come up, okay, and as we get close to uncoupled structure, it will smoothly transition to coupled structure, pass through the pressure release, go beyond, start following the next rigid duct cut on. Okay. Next, this uncoupled rigid duct cut on starts as a coupled rigid duct cut on, smoothly transitions to a coupled flexural wave, passes through the pressure release point, crosses over and becomes or gets asymptotic to the next rigid duct cut on, and so forth. Okay. So, this is the picture for small epsilon. Okay. So, here the structure sees the fluid as inertia and therefore wave number higher and therefore lambda lower. Okay. In this region, the structure does not see the fluid at this transition pressure release point. Here it sees it as inertia, here it sees it as stiffness. Okay. Here the original plane wave sees the structure as inertia. Okay. Less and less inertia, the wave number will drop. High inertia, you get back your uncoupled plane wave. In here, the fluid sees the structure as stiffness. Okay. Less and less stiffness, the wave number rises, kx goes up and lambda x comes down, so that wave speed goes down. And high stiffness, you approach the plane wave closer and closer. At almost infinite stiffness, you reach the plane wave back. Okay. And here, let us say for larger and larger values of epsilon, this curve will do this. For further larger values of epsilon, it will do this. Okay. Finally, it will become a correction to the pressure release cut on. It will become a correction to the pressure release cut on. Okay. And as epsilon becomes larger and larger, this wave will start moving up. This wave will start moving up. Okay. Now, just a point I want to make. You must have seen that at the first corrections, there is a blow up, the value blows up at these values, at these critical points. Okay. So, let us see, for omega, for a plane wave we took a correction A1 epsilon. For the flexure we took omega to the power half plus A1 epsilon. Okay. Now, I will show you, if I have lambda square root of omega square minus xi square, let us say. So, xi is here. So, xi square, okay, lambda square root of omega square minus xi square, which is omega square plus twice A1 epsilon omega plus A1 square epsilon square. Okay. So, if I cancel off etc., so what I get, lambda square root of omega square minus omega square minus twice A1 epsilon omega minus A1 square epsilon square. Okay. So if this cancels out, I have the leading term as lambda square root of minus twice a1 epsilon omega. Okay. Now when I approach a critical point, okay, there is a second root also that is approaching. There is a flexural root that is also approaching, just as the plane wave is approaching. Okay. So from the flexural root side also I have xi fourth over omega square minus 1. So in this I am going to substitute my omega to the power half plus a1 epsilon correction. Okay. So what that does is that I will have a correction term after cancellation which is of epsilon order. Okay. So here I have a correction of epsilon to the power half order. Okay. So this epsilon order correction and that epsilon to the power half correction will give me an epsilon to the power 3 by 2 order correction. There is also a tan term and just as this term gave me epsilon to the power half, this will be epsilon to the power half, and tan of that is also epsilon to the power half. So this epsilon to the power 3 by 2 and another epsilon to the power half and some terms plus epsilon should balance. But this has now become epsilon square and we are left with epsilon to be balanced. So it cannot be balanced. And so what now that means is that this expansion that we have, okay, should be of epsilon to the power half order. Okay. Then what happens is every correction term is half to the power half, then this will become epsilon and it can balance this epsilon from the fluid loading term. So what essentially means is that wherever you have two uncoupled roots meeting, you have a plane wave meeting a flexural. Okay. So there if two roots are meeting, you need to have half order expansions, so that the half order corrections from each of the roots multiply, they become epsilon, and then that epsilon can be balanced by this epsilon. Time is up. I will close here. We will continue with this topic in the next lecture. Thank you.